I want to cover one more example. We talked about insulin glucose. We talked about insulin glucose homeostasis. Let's make a model of that insulin glucose homeostasis, following the excellent work by Sturis and the group at the University of Chicago Medical School, endocrinology department. So we have two state variables, I and G, for insulin and glucose. And we start to make terms in the model. So let's look at the insulin I prime equation. What makes I go up? What makes I go down? What makes I go up, as we saw, is that when the pancreas sees glucose, it increases insulin production. And we're going to model that with a classic sigmoid. Again, this case, it's insulin production as a function of glucose. And it's going to look like a classic sigmoid. And the authors are using a fourth power here to indicate the correct level of sensitivity. So there's our glucose spurs insulin production by the pancreas. That's a sigmoid in G. It's an upgoing sigmoid in G. And then the down part is just, again, good old first order degradation of insulin that is metabolized and peed away and whatever. Now, what about the glucose equation? Well, G prime equals several things. Number one, what makes G prime go up is this term external, which is external glucose, like meals or infusions or whatever. And that's going to have whatever form it's going to have in a particular case. We also have good old degradation of glucose. There's an interesting piece of physiology that has to be built in here, which is that, as you see, insulin inhibits glucose production in the liver. And so we have a downgoing sigmoid here. As the more insulin there is, the less glucose is produced by the liver. And that takes care of that term. And then the last term is this one. And notice its form. It's our old friend, shark meets tuna, ST. This is glucose meets insulin. And glucose meets insulin in the muscle cell. And the glucose is metabolized by the metabolism of glucose is facilitated by insulin. And so the I meets the G, and that removes G from circulation. This is indeed like a shark tuna term. And indeed, a very deep analogy, and something I would be very happy if I heard somebody say, is insulin glucose? Why, that's just sharks and tuna. Because the dynamics really is very similar. Insulin meets glucose, and it reduces glucose. So now, here is our model. Let's ask how that model behaves. When we give, remember that external term here, when we give a glucose dose as our external term, that blue rectangle, the first thing that happens is glucose rises, and then insulin rises. And insulin rises. As soon as insulin begins to rise, glucose begins to go down, and the two go to equilibrium as the insulin reduces the glucose. Very nice, except not correct. And it's not correct because, once again, There are time delays in the system. You eat a meal, your blood glucose goes up. The insulin secretion by the pancreas is not instantaneous. It takes time for the pancreas to manufacture this complicated molecule called insulin, and there is therefore a time delay in the response of the pancreas to glucose in its production of insulin. So once again, we're in a situation where the insulin production term is not a function of current glucose. It's a function of what glucose was tau seconds ago when it was received by the pancreas. Now it's putting out insulin tau seconds later. So once again, we have to have a time delay term in the production term of insulin at the pancreas. And what happens when we include that time delay is the model output changes dramatically, and we now have insulin glucose oscillations. So the next question is, are there glucose insulin oscillations? And the Chicago group looked at it, and yes, indeed. There are insulin glucose oscillations. We already saw this slide. Under no meal conditions, we still see oscillations in insulin and glucose, and the period of those oscillations, which is 2 to 3 hours, is correctly predicted by the model. So here is a second mechanism. We talked about the hysterical parent and the too sensitive feedback, correct left, correct right. That's supersensitive feedback is one mechanism. And now we can state that the second mechanism is increased time delays. We've seen again and again how a system can maintain equilibrium with no time delays, but the minute the time delay is put in the system, then the system can go into oscillation. And if we want to go back to the parent teaching the kid to drive, this is a different parent. This is not the hyper-excitable parent. This is a parent who is so inattentive, maybe they're texting, that they take a long time to supply correction to the driver. So the driver starts to drift to the left, and the parent does nothing. And then maybe 10, 15 seconds later, the parent says, oh, you're drifting too far to the left, correct right. Driver corrects right. Passes the center line, and the parent takes a long time to get that feedback back to them. By this time, they're way past the center line, and they have to start correcting backward. So the introduction of time delays in a negative feedback system also produces oscillations. And a very interesting fact is the shape and the waveform of the oscillations that are produced by the N mechanism, by the sensitivity mechanism, have a different shape, different waveform than the oscillations which are produced by the tau mechanism. So let's leave that there as an example of oscillations in physiology being produced by two fundamental mechanisms: high sensitivity in a negative feedback loop and time delays.